Hello everyone. Finally we made it to the point where we can start talking about series. We have our tools necessary, and the first thing we have to make sure we understand is what's referred to as the summation operator. It's upper Greek letter sigma, and it means the sum of. So that's how you read it, the sum of, or to sum. When I make a sigma, it's going to look like this. Whatever you do, don't call it the big E thing or anything like that. Read it as the sum of. And now we define a series. Now, last time we talked about a sequence, which was a list of terms that followed a pattern established by the defining equation for the nth term a sub n. And the difference between a sequence and a series is that a sequence is just a list of terms, and a series is the sum of that list. So don't make this harder than it is. We read this as the sum as n goes from 1 to infinity of a sub n, and then if you were to expand it, you're just using the summation operator, letting n equal 1. You get the first term of the series, a sub 1. You have to go through the summation operator, so plus, and then the next term of the series would be when n is 2, and you'd get a sub 2, and so on. But notice that the terms are just simply added together. One thing to note is that we can start at 0 or any other integer, and if we're talking about a series in general with regards to some of our theorems, we'll just use the sum entity. So just remember the distinction. When we put a sub n in braces, that's a sequence. And when we have the sum of the a sub n, that's what we're going to use to represent a series. Okay, so now we want to find the sum of a series. And we consider what we refer to as the sequence of partial sums. And if the sequence of partial sums converges, then we say that the series converges. And we define the nth partial sum as just simply the sum of the first n terms. I guess actually I could have said s sub n here, okay? And if the sequence of partial sums converges, then we say the series converges, and the limit would be the sum of the series. And if the sequence of partial sums diverges, then we say the series diverges. So let's consider this series. The sum is n goes from 1 to infinity of 1 over 2 to the n by writing out the first 5 sequence. Well, we'll write out the first 5 partial sums, and then we'll consider the sequence of partial sums. So by writing out the first partial sums and the sequence of partial sums. Okay, so the first partial sum is just the first term of the series. 1 over 2 to the first, or 1/2. Second partial sum, the sum of the first 2 terms. 1 over 2 to the first plus 1 over 2 squared. So that's 1/2 plus 1/4, or 3/4. Third partial sum, 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed. Notice that's just the first 3 terms of the series, which gives us 1/2 plus 1/4 plus 1/8, which sums to 7/8. Fourth partial sum is 4. First 4 terms, 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed, plus 1 over 2 to the fourth, so 1/2 plus 1/4 plus 1/8 plus a 16th, 15 over 16, and finally the fifth partial sum of the first 5 terms, so 1 over 2 to the first plus, you could really just add 1 over 2 to the fifth onto the last partial sum, right? but this is showing it formally. So there's the first 5 terms, and that's a half plus a quarter plus an eighth plus a 16th plus 1 over 32, which adds to 31 over 32. So this can go on and on forever, but what we've established is, so those are the partial sums, and what we want now is to look at the sequence of partial sums. And remember, a sequence is just a list of terms. So if it's the sequence of these partial sums, it's a list of these results. The 1/2, 3/4, 7/8, 15/16, and 31 over 32. So 1/2 as a sequence, a list of terms, 3/4, 7/8, 15/16, 31 over 32. And that continues. So regarding the sum of this series, certainly we haven't proven it or anything, but looking at this sequence of partial sums, it looks like this sequence is converging to the number 1. So we're going to have more theory to be able to say that the sum of that series is actually 1, but for now that's what we've established. So then we come up with a couple theorems, which lead us to our first test for the convergence or divergence of a series. And we say that if the series converges, then the sequence converges to 0, which intuitively should make sense, because if the series is going to converge to some number, then the number that we're adding on as we continue here, like the 1/4, 1/8, 1/16, 1 over 32, the last number we're adding on is that term of the sequence. And if that's not tending toward 0, then the size of the sum is going to continue to increase without bound. So that certainly makes intuitive sense. For the second theorem, we say if the sequence does not converge to 0, then the series diverges, which is basically what I just got through saying, was that if you're adding on a number that's bigger, that's not tending toward 0, let's say this was tending toward 1, the number that we're adding on every time. If we added 1 onto the sum of a series an infinite number of times, then the sum's going to approach infinity. And that leads us to our first test, and for convergence or divergence of a series, and it's referred to as the nth term test for divergence. I cannot stress enough that this does nothing for you with regards to convergence. It's just a test for divergence, and it basically says mathematically what we were saying in these two theorems. If you take the limit, so this is the sequence, okay, if the nth term of the sequence is not 0, then the series will diverge, okay? So all you have to do is look at the limit of the nth term. If it's not 0, then it's going to diverge. And this looks like it's an X, that should be an N. Okay, now mentioning this, that there's a table of the basic test for series that I posted in Blackboard under exam 4. I think it's called homework and handouts, actually. This is what it looks like. It has all the different tests for series that we're going to encounter. And notice how it's constructed. It has the type of test, the type of series, the name of the test, I should say, in the first column, the type of series we're dealing with in the second column, the statement regarding its convergence or divergence, and then a comment. And basically, for this nth term test, you can see it's the first row here. It says it's good for any series, and it diverges if the limit of as n goes to infinity of a sub n is not 0. And that's exactly what we said here. The limit's not 0, it diverges. But then it says, under the comment section, it's inconclusive if the limit is 0. Okay? So we'll see some examples. So you could use this, I would suggest you use this table as you work through your homework for reference. You will be allowed to use this on the final exam, and you could write, and this will be your ultimate self-created cheat sheet for the final exam. That is, you can write anything that you want on the back of this paper. It's an 8.5 by 11 sheet of paper. Write anything that you want on the back of the paper and bring it into the final exam with you. Okay? So you can create your own personalized cheat sheet, and you have this table at your disposal. So we'll be referring to this table as we progress through our topics, but I just wanted to introduce it now, and I mentioned about the cheat sheet here as well. Okay, so a couple examples. And again, don't make this more difficult than it is. Just follow the rules. If you could read that table, you're going to be fine, because all it says is use the nth term test to prove divergence if possible. And if you look at the table, okay, so let's say you're in the final exam, you see this question. I'm going to tell you for the majority of the situations what test to use. So I'm telling you nth term test. So therefore you go to the appropriate row, there's the nth term test. You look at the conditions, it says check out the limit. So let's look at the limit as n goes to infinity of a sub n. And that's the limit as n goes to infinity of n over 2n plus 1, or 3, excuse me. And we just calculate that limit. Okay, here's the special rule that we talked about. Polynomials, degrees are equal, they're both 1. Limit's going to be the ratio of the leading coefficients. So we don't have to use L'Hopital's rule. You could if you want. That limit is 1/2. Obviously not equal to 0. And so therefore we could say that our series diverges. And that's all there is to it. So, a very simple test. Okay, next example, same idea. Take the limit as n goes to infinity of 1 over n. But here's a problem, because if you plug in infinity, you get 1 over infinity, and in a limiting sense, division by infinity, recall, is 0. So therefore, the test is inconclusive. So we need more to go on. And we'll establish the theory shortly that tells us what that very famous series 1 over n does. Okay, that was topic 1. That's all there is to that topic. We're going to go to topic 2 right away here and try to finish both in this one video. And we look at a special type of series. It's called a geometric series. And here's the idea. A geometric series is a series such that each term is the product of this common ratio, r, and its preceding term. And so let's develop the formula based just on that deal, or on that idea. And let's say this, let a equal the first term of the series. So the first term in the series is going to be a. The next term is going to be that common ratio times the preceding term a. So AR. Next term, R times AR squared. Next term plus, because it's a series, so adding the terms together. So next term plus AR squared times AR cubed. Next term of the series plus AR cubed times AR to the 4th, and that goes on forever. Now what we want is a summation notation for this. And you can represent it in one of two ways. It could be the sum as n goes from, okay, if you want to start at 0 to infinity, it would have to take the form of ar to the nth power. Because then when n is 0, you get r to the 0, which is 1, times a, so you get a. Then when n is 1, you get ar to the first, or ar. When n is 2, you get ar squared, or ar squared, and so on. Another representation that is often used is to start at an index of 1. And if you start at an index of 1, in order for the first term to be a, the power on r cannot just be n. It would have to be, in order for r not to be in the first term, when n is 1, the power on r would have to be n minus 1. Because then, when n is 1, this would be r to the 0, which is 1 times a, gives you first term a. When n is 2, ar to the 2 minus 1 is 1, so that's ar. When n is 3, we'd have ar to the 3 minus 1, or ar squared, and so on. So those are the two general representations for a geometric series. And you can see that what I've done on the table there is, under the geometric series, I squeezed in the little sum as n goes from 0 to infinity of ar to the nth, because they didn't have that. They only had n equaling 1 to infinity, ar to the n minus 1th. But we're going to get to the convergence, divergence, and the theorem. An example of what this looks like is maybe the sum as n goes from 0 to infinity of 3 times 2/5 to the nth. That's just an example of what the infinite geometric series would look like. It's really just a number, typically is a fraction, raised to a power. Now notice that n is 0, and here the power on the common ratio r matches the appropriate form. Okay, so, or maybe if you had the sum as n goes, I'm just giving examples of what they look like. I don't know, 7 times 3/4 to the n minus 1th. Notice how in my examples here, let me separate that theory from this. Notice how I'm making the index match the appropriate power on r so that it fits one of the standard forms. We'll see an example momentarily where that doesn't work. Here's the theorem regarding convergence or divergence. It's basically just based on the common ratio r. You just look at what r is, and you should be able to pick that out easily. Just match it up. And if r is less than 1, it's going to converge. And this is actually the sum that it's going to converge to. And if the absolute value of r is greater than or equal to 1, it diverges. And that's all there is to it. So let's prove this sum formula. Not that I'm going to hold you accountable for this, but I think it's a nice thing to see. We're saying that the sum of the series is represented by this: a plus ar plus ar squared plus ar cubed, ar to the 4th, and so on. We're saying that's our sum right there. So S equals a plus ar plus ar squared plus ar cubed, and so on. What I'm going to choose to do here is I'm going to multiply everything by r. So I'm going to have rs equaling, and so I'm going to distribute the r and multiply all of these by r. So I would get ar plus ar squared plus ar cubed plus ar to the 4th, and so on. And then I'm going to subtract. I'm going to subtract the bottom from the top. And on the left-hand side, we just have S minus RS. And on the right-hand side, look what happens. Every term except for this first term A gets eliminated. Because this AR minus this AR squared minus that AR squared, AR cubed minus that AR cubed. This is infinite. There's an AR to the fourth right there that goes away with that one. And everything else vanishes. So that's all we have. And then if we factor out the S, we're left with S times the binomial quantity 1 minus R equaling A, and dividing by 1 minus R, we've actually proven the formula. Okay, so some examples. And look at the table. Feel free to look at the table and get familiar with that. It says the same thing we said, converges to the sum. A is 1 over n minus r. If r is less than 1, r is greater than or equal to 1, it diverges. Just make sure it matches with one of the standard forms. Like when I look at this, I consider the standard form where the index starts at 1, and it has to be of the form AR to the n minus 1th. And it is. Because the index is 1, and the exponent on that common ratio R is n minus 1. So look at the absolute value of R, which is the absolute value of negative 7 halves, which is 7 halves. Obviously that's greater than or equal to 1. So then it diverges. And that's all there is to it. Same idea with the second example. Just make sure it matches. We'll see in the third example when it doesn't match what we need to do. Okay, it's AR to the nth. This is the standard form when n starts at 0. And so everything fits. The absolute value of R is the absolute value of 2/5, which is 2/5, which is less than 1, so it converges. And moreover, because if you read the directions, determine convergence or divergence. If it converges, find the sum. It converges to the sum of A over 1 minus R. And this is where the value of A is just match it up. Don't make it harder than it is. AR to the nth. A is 3. We already know that. If you wanted to restate it, R is 2/5. So the sum would be A3 over 1 minus 2/5. Okay, here's the hard part, 5th grade arithmetic, fractions, 3 over 3/5, 3 times 5/3, gives us 5. So that's it, that's the sum. Now I'm going to put a little wavy line here. I just want to show you something for fun. Let's say, let's write out the terms. Because what we're saying is, no matter how far out you go, you add on an infinite number of terms, this thing's never going to exceed 5. And if you look at the terms, okay, so we'll say the sum is, alright, when n is 0, we get 3 times 2/5 to the 0, or 3. When n is 1, we'd get 3 times 2/5, so 3 times 2/5 to the first, 3 times 2/5, 6/5. When n is 2, 3 times 2/5 squared. 2/5 squared is 4 25ths times 3, 12 over 25. Next term, when n is 3, we'd get 2/5 to the third is 8 over 125 times 3, 24 over 125. And if you just add those up, it's kind of amazing that what happens, let me just add them here real quick, 3 plus 6 fifths plus 12 over 25 plus 24 over 125. These, just the first four terms added together, give 4.872. So it's kind of amazing to think that no matter how far out you go, you're never going to exceed 5. Because what's happening is the denominator is growing at a rate relative to the numerator that the terms are never going to add on to make this larger than 5 units. Okay, last question real quick. I'm going to give you something like number 2 on the exam, and so something really easy, just find the sum. Here, remember I was talking about matching. This is just to help you with the homework a little bit, because I know there's at least one question here. If it starts at 1, then we're talking about making sure you match, the power has to be n minus 1. Okay, so this is not the same. So what we have to do is we have to modify. So here's the little trick. My only other choice in this case to make this match would be to start at 0 to match one of the 2 basic forms. Now this is what I call an exponential shift, or this is what I call I'm going to call this not an exponential shift. This is what I call a shift of the indices. What I'm going to do is I'm going to drop down the value of n. I'm going to decrease n by 1 and make it 0. But if I decrease that by 1 to compensate, I have to increase the value of n in the expression for the defining equation of the nth term. So that becomes n plus 1. Then what we could do is rewrite this as 3/7 to the n times 3/7 to the first. Because that's common bases being multiplied together. If you multiply bases, you add the exponents. So I basically just use the rule for, let's say, x to the a times x to the b, which is x to the a plus b. I use that in reverse to write this as 3/7 to the n plus 1 to be equal to 3/7 to the nth times 3/7 to the first. This was just a side, just to show you what we did. Okay, so then we could bring the 3/7 and the 5, call this 15ths, so the sum is then goes from 0 to infinity of, we could say 15/7 times 3/7 to the nth, and now it matches. That is, this is the sum as then goes from 0 to infinity of AR, and now it matches the appropriate power, the nth power. Okay, so the absolute value of R is the absolute value of 3/7, which is 3/7, which is less than 1. Look at the theorem if you have to, and it converges. Okay, and you can find the sum if you'd like, but I want to stop right there because we're at 30 minutes and I might have a time limit on YouTube. So find the sum if you like.